This is the video submission for Team 1037. Our team members consist of Vance, Hayley and Allison Wilke. Our team coach is Dr. Matthew Kipper, and we are associated with Colorado State University in Fort Collins, Colorado. We decided to analyze and develop a model for problem statement C, dog cannot catch. In order to solve this problem, we first split it up into different sections to analyze and then made assumptions in order to create a model to depict the situation. The first section we considered is the throw from the owner. The assumptions made are that a constant force is applied for 1 unit length during the underhand throw. All the forces generated by the arm goes into propelling the object. The throw reaches the dog, and the owner's hand extended straight down is positioned level with the center of the dog's head, and finally the thrower is an average male while Fritz is an average-sized golden retriever. The next assumptions we made are for the food's motion. We limited the food to a 2D plane so that there is no lateral movement. There is negligible rotational motion and an absence of external drag forces. Additionally, the food sustains constant velocity post point B, meaning the acceleration upon entry into the dog's mouth is negligible. Finally, the assumptions made for the dog are as followed. The dog's head adjusts to the correct position immediately after a delay of 150 milliseconds. The dog possesses standard visual acuity. The dog will remain grounded and not jump during the catch. The pivot point of the dog's jaw is 39.3701 inches horizontally from the owner throwing and at a 0 height vertically according to our axes. And lastly, the dog's jaw spans 5 inches and has a 5-inch open mouth clearance. The goal of this problem is to mathematically model the situation to decide if Fritz is just being clumsy or if his owner is being mean to go viral on the internet. To do this, we wanted to investigate how the angle at which the food is thrown affects the path to Fritz, ultimately evaluating the likelihood of Fritz successfully catching the food in the end, and overall developing a model to provide recommendations for Fritz and his owner to lead to more success. This is the problem setup referenced throughout our assumptions and calculations. As seen here and mentioned before, the ground state is level with the dog's mouth and the owner's hand extended downwards. Additionally, these are the constants and their units used throughout the equations developed for the model, which are gravity, length of the jaw, length of the arm, and the target distance, which we chose to be 1 meter.
Our model has the dog's mouth as a range of points rather than just 1 point. As such, it has certain catching requirements. First, the object needs to be positioned above the bottom jaw. Next, the object's trajectory slope needs to fall within the limits defined by lines C and D. If it doesn't fall within there, it's going to not land in the mouth. Next, the trajectory slope needs to be negative. The object, in the way it is being thrown, is going to be coming from above, not below. Next, the time of impact must exceed the dog's delay time, so it has enough time to react and catch the ball. And lastly, we are assuming that the object has constant velocity after passing point B.
In regards to calculations, the first thing we needed to find was the initial velocity. In order to do this, we combined kinematic equations for projectiles. In doing so, we were able to get 2 equations with only 3 unknowns, factoring in our known values of x and y. These unknowns were initial velocity, time, and theta, and we knew that we were going to decide theta by using a vector of values, so we were able to use the MATLAB symbolic equation solver and the built-in function solve to find the initial velocity as a function of angle, which we could use by implementing a vector or by implementing it into our for loop.
To set up our calculation, we ran 2 for loops. The outer loop varies the variable theta, which goes from 10 degrees to 70 degrees. In this outer loop, we will then calculate the needed initial velocity to get to the dog, and any variables that vary with theta will be indexed with the letter J. For our inner loop, we varied the value of phi, which in our case runs from 60 to 70 degrees. We chose these numbers because there is a 60-degree difference between points A and B, and we wanted YB to be greater than or equal to 0 for all values of phi, while also not having the dog strain its neck. Values that change with phi are indexed with the letter I. Using basic geometry, we can find YA, YB, XA, and XB. Next, we are going to find the time at which the object arrives at x equals b. The equation we used for this is F equals ma as a differential equation of x, solving for x. We use the analytical solution to find this. We then plug that time into the analytical solution for the position of y to find where the object is located vertically. These are both indexed with letters J and I. Lastly, we are going to calculate the values theta A and theta G. Theta A is the angle between the object and A. We find this using geometry. Theta G is the angle of the velocity of the object at B. Because velocity is the derivative of position, we use the velocity of x and the velocity of y to find the angle of the velocity. Finally, we can quantify success. As a reminder, success requirements needs the theta g to be less than 0, so the object needs to be heading down. The object needs to be above the bottom jaw. The object angle needs to be between negative 90 degrees, so straight down, and theta a. And lastly, the time of impact needs to be greater than the delay time of the dog. If all of these requirements are met, then the success matrix for Ji will be given the value of 1. If not, it is given the value of 0. After the loop has finished, we can then calculate the fraction of success. So we will sum the success, the row J of the success matrix divided by the length of the success matrix, and that will tell us how many of the angle phi's worked for catching the ball. If the fraction of the success is higher, then there are more ways for the dog to catch the ball, and it is more likely to be able to catch it. Lastly, we calculated a derivative of the fraction of success with respect to the angle thrown at. We used finite difference methods to do that. We used a 2-point central difference method, and then 3-point forward and backwards difference methods for the edges of the data points. We found that the best angle to throw the object at is 14 degrees, as that corresponds with a maximum on the other graph, and with the value 0 on this graph.
This model has given us a lot of insight into how the angle at which the food is thrown at impacts the ability of Fridge to catch the food. So our advice to the owner, if you'd like to actually train Fitz on how to catch food, our advice to you is to throw the food at a less deep angle, as this has shown that it gives him the best probability at being able to actually catch it. This is mostly due to the fact that at this low theta, most of the velocity is in the horizontal component, so there's very little work for the dog to do to actually catch the food, and the food goes basically straight to him. However, if you would like to continue to go VIII, I recommend you throw it at a steep angle, as that gives the dog the least chance in being able to catch the food. And you'll be able to continue making funny videos of a dog being very bad at catching snacks. In analyzing our model, we have found that the model has a lot of great successes, but has a lot of associated limitations as well. One of our major successes is we were able to find a range of combinations of theta, which is the initial angle the food is thrown at, as well as phi, the rotation of the dog's head, to account for a probability of the dog catching the food over a variety of conditions. However, one of the limitations of this model is that it is only in 2 space instead of rotating side to side. It is only in the X and Y plane. And in order for this model to work, we had to make many assumptions, including neglecting drag, always assuming that the food is going to be directly thrown to the dog, and many of these limitations means it may not be completely applicable to the real world. In order to make this more applicable to reality, we do know a little bit of the future direction of this model. Improvements could be made by moving into 3 space and incorporating that lateral movement in the XZ plane. We could also account for drag within the model, as well as accounting for the food and its associated effects of changing the shape, mass, as well as factoring in the rotation of the food. One of the things we did not allow within our model is that the dog could not jump or move. Allowing for that movement would make this model more applicable to the real world and make it more accurate. We also did not allow for varied force or
any torque on the object, so factoring that in would increase its reality. Another thing to factor in that could make it more realistic would be allowing for velocity to not be optimized and for the velocity to not allow it to reach the dog 100% of the time.